In section 10.1, we talked about how we create our initial hypotheses, the null hypothesis and the alternative hypothesis, H1, and how we write our conclusions. Now let's talk about how we actually conduct a hypothesis test for a population proportion. So when performing tests of hypothesis for a population proportion, which we call P, the null and the alternative hypothesis looks like this. The null hypothesis is P equals P sub 0. And the alternative hypothesis is P, and remember we have three options, either not equal, less than, or greater than P sub 0. And P sub 0 is the hypothesized proportion. So that's the number we're testing that comes from the problem. The calculations are based off of the sampling distribution of P hat. And remember, any sampling distribution is approximately normal as long as the sample size is big enough. There are three requirements we need to test the hypothesis. The sample has to be a simple random sample. We have to have that the sample size times the sample proportion times, sorry, not the sample proportion, the proportion that we're going to test times 1 minus the proportion we're going to test has to be greater than or equal to 10. So remember, lowercase n is the sample size, and P0 is the hypothetical proportion. And the sampled values we have need to be independent of each other. So remember, from way back in chapter 5, we can treat events as independent if the sample size is less than 5% of the population. So if we use notation to express that, lowercase n, which is the sample size, is less than or equal to 0.05 capital N, and capital N is the population size. So we need to talk about statistical significance. When observed values are unlikely, under the assumption that the null hypothesis is true, we say the result then is statistically significant. And then we reject the null hypothesis. In other words, convincing evidence against the null hypothesis is statistically significant evidence. We're going to use what we call the p-value approach of hypothesis testing. So let's talk about the logic of this approach. The method we use, this p-value approach, is to determine how likely it is to obtain the observed sample proportion. So the calculator or StatCrunch is going to give us what we call a p-value. Now, important here, a p-value is a probability. So it has to be between 0 and 1 inclusive, just like all probabilities. So the p-value is the probability of observing a sample statistic as extreme or more extreme than the one observed under the assumption that the statement in the null hypothesis is true. So to put it in a little bit more plain English, the p-value is the likelihood or probability that a sample will result in a statistic such as the one we've observed if the null hypothesis is true. So, of course, we're going to use technology. We can use TI 8384, or we can use StatCrunch to do this. So, the formal definition for hypothesis testing using the p-value approach is: if the probability of getting a sample statistic as extreme or more extreme than the one obtained is small, under the assumption that the statement in the null hypothesis is true, then we reject the null hypothesis. How do we know how small it has to be? Well, that's based on the level of significance. That we choose. And that level of significance can be thought of as the cutoff value. So anything smaller than the cutoff value means we reject the null hypothesis. So the level of significance is denoted alpha, and alpha is almost always given in the problem. So we always compare the p-value with alpha. If the p-value is less than alpha, we reject the null hypothesis. So we reject the null. If the p-value is greater than or equal to the level of significance, then we do not reject the null. And there's a silly little thing we can use to help us remember. It says if the p is low, the null must go. So that tells us that we reject the null hypothesis if the p is lower than the p-value is lower than alpha. So we'll talk about the process of doing this in just a minute in the next video.